Alright, so in this video we're just going to talk about the scalar triple product. Now, this is a bit mind-bending, but we need to be able to work inside of 3D to understand what the scalar triple product is doing for us, what it's giving us. So, here I have three vectors. So, vector A is 1, 2, 3, vector B is -2, 2, 1, and C is 1, -2, 1. This is my I, this is my J, and the blue is my K. And we've got our three vectors. Now what I'm going to do is create a parallelogram between two of those vectors. So let's take a look at what that parallelogram looks like first of all. So here's my parallelogram. Now I can also draw another parallelogram between another set of those vectors. So let's do that. So here's another parallelogram between two of the vectors. So now I've got two parallelograms, you can see there. Okay, stay with me. Now we can draw a third parallelogram between these two vectors. So let's take a look. We've got one parallelogram between those two, a parallelogram between these, and a parallelogram between these. Now we can finish this whole thing off by closing up this 3D shape. So a parallelogram, a parallelogram, a parallelogram. So now, hopefully you're seeing this in 3D, you can see we have a 3D shape made of parallelograms. This has a very, very special name that's a bit weird. It is a parallelepiped, a solid body of which each face is a parallelogram. So to find the volume of a parallelepiped, you need to use the scalar triple product. So let's find the volume of this parallelepiped using those vectors. So to find the volume of my parallelepiped, I'm going to use the scalar triple product of these three vectors. So, quick formula, scalar triple product is equal to A dot B times C vectors. So it's the vector product here and then the dot product of A. You've kind of got to work backwards here, because if you think about what the result of this is going to be, remember that a dot product results in a scalar, just a number, whereas the vector product results in a vector perpendicular. So if you did it the other way, if you did A dot B, you'd end up with a scalar, and then if you tried to multiply it by C, it would be a mess. So you don't have to draw in brackets, but that's essentially what you're doing. A dot B times C. Now what's that going to give us? Well, B times C, vector B times C, if I go back to our drawing, that's going to give me the area of a vector of a parallelogram described by vector B and C. Now when I multiply it by A, what I'm actually doing is multiplying it by the perpendicular height of this shape. So pretty simple volume calculation, and we're going to do it in a fairly straightforward way. We're going to do it using determinants again. So A dot B times C equals the determinant of this vector, A1, A2, A3, B1, B2, B3, C1, C2, C3. So I'm just going to write all of that in now. Okay, so you've done the determinant before. Last we did I, J, and K, and you end up with a vector, I, J, and K. This time, because it's all numbers, when we multiply this, when we find the determinant of this, what we're going to end up with is just a number, which is going to be the volume of our scalar triple product. Sorry, the volume of our parallelepiped. All right, you should know how to do this, so I'm going to try to get through it. Okay, so that's it. That's the end of this whole game. The volume of my parallelepiped is going to be 12 units. Last thing I'll note here is if you do things in a different order, something you're going to end up with is probably like a -12. So really we've got to say that when we do it, the scalar triple product is used for a few things, but when we use it for volume, we're going to have to do like an absolute value. A dot B times C. That's it.